Metabolism and nutrition basis principle. Main clinical use of maternal in this chapter are the functional nutritional counseling to lose weight using fat diets, proteins and diabetic diet proteins with the nutritional misinformation proteins with anorexia, patient with chronic disease, patient with metabolism problems, and ordering appropriate diets for hospitalized patients. There is a real elderly, those with end-stage organ disease, those of intravenous nutrition or tube feeding. Understanding the basic fuel metabolism is critical to understanding normal human functioning, and recognizing the abnormalities in the basic fuel metabolism will allow the diagnosis and treatment of the wide variety of disorders. Overview. Major fuels of the body, carbohydrates, fats, and proteins, are obtained from the diet and stored in these body fuel depots. In the fed state, after a meal indigestion, fuel is used to meet the immediate energy needs of the body, and excess fuel is stored in either glycogen and triglyceride. During fasting, between meals overnight, stored fuels are used to derive the energy needed and to survive until the next meal. To prolong fasting, starvation, change occur the use of fuel stores the patient's survival for extended periods. Level of insulin in the blood increase in feed site and promotes the storage of fuel, whereas the level of glycogen increase the fasting state promote the release of stored fuel. Metabolism, fluid and dietary components. Carbohydrates, fat, proteins survive as the major fuels of the body and obtained from the diet. After digestion absorption, these fuels can be oxidized for energy. The fuel consumed in excess the body's immediate energy needs is stored mainly as fat but also as glycogen, a carbohydrate stored molecule. To some extent, body fluid can also be used as fuel. The daily energy expenditure of an individual includes the energy required for the basal metabolism rate and the energy required for physical activity. In addition to providing energy, the diet produces the precursor for the synthesis of structural components of the body and supplies essential compounds that the body cannot synthesize. Essential fatty acid, amino acid, vitamins, and minerals that often serve as cofactors for enzymes.
BRS, Biochemistry, Molecular Biology and Genetics, Fuels. Why fuels are metabolized in the body? Heat is generated and adenosine triphosphate ATP is synthesized. Energy is produced by oxidizing fuels to CO2 and H2O. Carbohydrates, when completely oxidized, produce about 4 kilocalories per gram. Proteins, when completely oxidized, produce 4 kilocalories per gram. Fat, when completely oxidized, produce more than twice as much as energy, 9 kilocalories per gram. Alcohol, present in many diets, produce about 7 kilocalories per gram when completely oxidized. Physicians and nutritionists often use the term calorie in place of kilocalorie. The heat generated by fuel oxidation is used to maintain body temperature. ATP is generated by fuel metabolism, is used for biochemical reaction, muscle contraction, and other energy requiring processes. Composition of the fuel stories: triglyceride, adenosine triglycerol is the major fuel stored in the body. Adipose tissue stores fuel very efficiently. It has more stored calories per gram, less water, air, less water 15% than do other fuels. Muscle tissue is more than 80% water. Glycogen stores, ultra small, are extremely important. Glycogen stores, ultra small, are extremely important. Liver glycogen is used to maintain blood glucose levels during the early stages of fasting. Muscle glycogen is oxidized for muscle contraction. It does not contribute to the maintenance of blood glucose levels under any condition. Protein does not serve solely as a source of fuel. Protein does not serve solely as a function of fuel and de- can be degraded only a limited extent. Approximately one third of the total body protein can be degraded. If too much protein is oxidized for energy, body functions can be severely compromised. DEE is the amount of energy required each day. BMR is the energy used by a person who has fasted for a last 12 hours and is awake but at rest. A rough estimate for calculating the BMR is as follows: BMR to 14 kilocalories kg body weight per day. Diet include thermogenesis is the elevation in metabolic rate that occurs during digestion and absorption of food. It is often ignored in calculations because its value is usually unknown and probably small, less than 10% of the total energy. Physical activity. The number of calories that physical activity adds to the DEE varies considerably. A person can expend the 5 calories each minute while walking, about 20 calories while running. The daily energy requirement for an extremely sedentary person is about 30% of the BMR. For a more active person, it may be 50% or more of the BMR. The thyroid gland produces thyroid hormone, which has profound effect on a person's BMR. One of the most common forms of hyperthyroidism is Graves' disease. In its disease, the body produces antibodies that stimulate the thyroid gland to produce excess thyroid hormone. In disease is characterized by elevated BMR, an enlarged thyroid goiter, and protruding eyes, nervousness, tremor, palpitation, excessive perspiration, and weight loss. Saccharide and hypothyroidism result from a deficiency of thyroid hormone. The BMR is decreased, and micropolysaccharides accumulate on the vocal cords and is subcutaneous tissue. The common symptoms are lethargy, dry skin, a husky voice, decreased memory, and weight gain. The body mass index is the utilized to determine a healthy body weight. The BMI is defined
as the volume obtained when the weight in kilogram is divided by the height in meters squared. BMI is kilogram per meter square. They indicates the interpretation of the BMI value. তাহলে কি body mass index is utilized to determine the healthy body weight. BMI is defined as the value of obtained when the weight is divided by the height. Weight is divided by the height, kg per meter square. The clinical correlates. There are a number of disorders related to the abnormal BMI value, some of which are the lifestyle induced obesity is associated with problems such as the hypertension, cardiovascular disease, and type of 2 diabetes mellitus. The treatment involving altering the lifestyle, particularly by decreasing food intake and increasing exercise. Type 2 diabetes is the result of weighing the compared with normal. Anorexia nervosa is characterized by self-induced weight loss. Those of frequently affected include the woman, who is in spite of initiated appreciate often claim to be frequency affected. They include fat. It is partially a behavioral problem. Those affected are obsessed with losing weight. People with bulimia suffer from bingers of overeating, followed by the self-induced vomiting to avoid the gaining weight. Other dietary requirements of recommendation for normal adults: lipids, fat, cholesterol, and essential fatty acid. Fat should consist between 20% and 35% of the total calories, with structured fatty acid according for 10% or less of that total. Cholesterol intake should be no more than 300 mg per day for healthy individuals, or less than 200 mg per day in those with established linoleic acid or alpha or linoleic acids are the precursor of the polyanosal
polyunsaturated fatty acids. Polyunsaturated fatty acids required for synthesis of prostaglandins and other eicosanoids such as arachidonic acid and eicosapentaenoic acid. These essential fatty acids can be found in high levels in fish oils. BRS, biochemistry, molecular biology and genes. Protein. The recommended protein intake is 0.8 gram per calorie body weight per day. Protein can be a high or a low quality. High quality protein contains many of the essential amino acids and usually obtained from dry beans and meat, chicken or fish products. Low quality protein is found in many vegetables. It lacks some of the essential amino acids required for human diet. Clinical correlates. A number of diet plans call for high protein diets. When high protein diets are very low in calories and the protein is low biologic value or quality, i.e. lacking in essential amino acids. Negative nitrogen balance results. Body protein is degraded because amino acids are utilized for new protein synthesis of the carbons converted to glucose. A decrease in heart muscle protein can lead to death. Even if the protein is high quality, ammonia and urea levels risk putting increased stress on kidneys. Vitamin deficiency may occur because of lack of intake of fruit and vegetables. Essential amino acids. 9 amino acids can be synthesized in the body and must therefore be present in the diet cannot be synthesized in the body and must therefore be present in the diet in order for protein synthesis to occur. These essential protein acids are histidine, isoleucine, leucine, lysine, methionine, phenylalanine, threonine, tryptophan and valine. Only a small amount of histidine is required in the diet. However, larger amounts are required for growth, i.e. for children, pregnant women, people recovering from injuries. Because arginine can be synthesized only in limited amounts, it is required in the diet for growth.
dietary proteins. It's about 60% nitrogen is the body's primary surface of nitrogen. Proteins are constantly being synthesized and degraded in the body. As amino acids are oxidized in the nitrogen is converted to urea and excreted by the kidney. Other nitrogen containing compounds produced from amino acids are also excreted in the uric acid, creatinine, and NH4. Nitrogen balance. The normal state in the adult occurs when the amount of the nitrogen excreted in the urine each day because of amino acid degradation equals the amount of nitrogen ingested daily in the form of amino acid. A negative nitrogen balance occurs when the degradation of the body protein excretion of the nitrogen exceeds the amount of nitrogen ingested. In result from the inadequate amount of protein in the diet absence of the one or more essential amino acid. A positive nitrogen balance occurs when the degradation of body protein and loss of nitrogen are less than the nitrogen ingested for the synthesis of new protein. It occurs during growth and synthesis of the new tissue. Carbohydrate. There is no requirement for carbohydrates in the diet because the body can synthesize all required carbohydrates for amino acid carbons. A healthy diet should consist of 45% to 65% of the total calories in the diet as carbohydrate. Vitamins and minerals. Vitamins and minerals are required in the diet. Many serves the cofactors for enzymes. Minerals required in large amounts include the calcium and phosphate, which serves as structural components of bone. Minerals requirement in trace amounts of include iron, which is a component of heavy. Major electrolytes are sodium, potassium, and chloride. Magnesium is often required for energy that utilize ATP. Trace minerals include the iodine, selenium, copper, zinc, iron, whereas the alternate minerals and manganese, fluorine, chromium, and the molybdenum. 9 amino acids cannot be synthesized in the body and must therefore be present in the diet in order for protein synthesis of occur. These essential amino acids are histidine, isoleucine, leucine, lysine, methionine, phenylalanine, threonine, tryptophan, and valine. Only a small amount of histidine is required in the diet. However, larger amounts are required for growth, for children, pregnant women, people recovering from injuries. Because arginine can be synthesized only in limited amounts, it is required in the diet for growth. Nitrogen balance. Dietary protein, which contains about 16% of nitrogen, is the body's primary surface of nitrogen. Proteins are constantly being synthesized and degraded in the body. As amino acids are oxidized, the nitrogen is converted to urea and excreted by the kidneys. Other nitrogen containing compounds produced from amino acids are also excreted in urea, synthesized only in limited amounts. It is required in the diet for growth. Nitrogen balance. Dietary protein, which contains about 60% nitrogen, is the body primary source of nitrogen. Proteins are constantly being synthesized and degraded in the body. As amino acids are oxidized, the nitrogen is converted to urea and excreted by the kidneys. Other nitrogen containing compounds produced from amino acids are also excreted in urine, uric acid, creatinine, and ammonia. Nitrogen balance. The normal state in the adult occurs when the amount of nitrogen excreted in the urine each day because of amino acid degradation equals the amount of nitrogen ingested daily in the form of amino acid. A negative nitrogen balance occurs when degradation of body protein and excretion of nitrogen exceed the amount of nitrogen ingested. It results from an inadequate amount of protein in the diet or from the absence of one or more essential amino acid. A positive nitrogen balance occurs when degradation of body protein and loss of nitrogen are less than the nitrogen ingested for the synthesis of new protein. It occurs during growth and synthesis of new tissue. carbohydrate. This is no requirement for carbohydrates in the diet because the body can synthesize all required carbohydrates from the amino acid carbons. A healthy diet should consist of 45% to 65% of total calories in the diet as carbohydrates. Vitamins and minerals. Vitamins and minerals are required in the diet. Many serve as cofactors for enzyme. Minerals requires large amount of calcium and phosphate, which serve as a structural component of bone. Minerals require in trace amount of induced iron, which is component of Heme. The major electrolytes are sodium, potassium, and chloride. Magnesium is often required for enzymes that utilize the ATP. Trace minerals include iodine, selenium, copper, zinc, and iron, whereas ultra trace minerals are manganese, fluorine, chromium, and molybdenum. তারপর হচ্ছে ফিট অফ অবস্ট্রাকটিভ কি absorptive state. Fade of absorptive state. Dietary carbohydrates are delivered during digestion from the monosaccharide, mainly glucose, which enter the blood. Glucose is oxidized by virus tissue for energy or stored as glycogen in the liver and in the muscle. In the liver, glucose is also converted to triglyceride, which are packaged in very low density lipoproteins and released into the blood. Fatty acids of the VLDL are stored in adipose tissue. Dietary fats. Triglycerides are digested to fatty acid to cycloglycerol to monoglycerides. These digestive products are resynthesized to triglycerides by the intestinal epithelial cell, packaged in cyclomicrons, and secreted via the lymph into the blood. Fatty acid of cyclomicrons are stored in adipose triglycerides. Dietary cholesterol is absorbed by the intestinal epithelial cells and then follows the same fate as the dietary triglycerides. Dietary proteins are digested to amino acids and absorbed into the blood. Amino acids are used by various tissues to synthesize proteins and to produce nitrogen-containing compounds, purines, heme, creatinine, epinephrine, or they are organized to produce energy. Digestion and absorption. Carbohydrates. Starch. The storage form of carbohydrate in plants is the major dietary carbohydrate. The salivary alpha amylase in the mouth and pancreatic alpha amylase cleavage search to disaccharide and oligosaccharides. The fade state. The critical number serve as guide the indicating the approximate order the process being to occur. A amino acid, acetyl CoA, acetyl coenzyme A, ATP, adenosine triphosphate, COH carbohydrate, Fa fatty acid, insulin, red blood cells, and tricarboxylic acid and triglycerol and very low density proteins stimulated by time with maltase and isomaltase activities such as the glycomylase are found in complexes located on the surface of brush border of the intestinal epithelial cells. They complete the conversion of starch to glucose, sucrose and lactose. Conversion of starch of glucose, sucrose and lactose. Indigested disaccharides are cleaved by enzymes that are part of the complexes located on the surface of intestinal epithelial cells. Sucrose. As part of the sucrose isomaltase complex converted sucrose to fructose and glucose. Lactulose converts lactulose to glucose and galactose. Monosaccharides, mainly glucose and same fructose and galactose, are absorbed by the intestinal epithelial cells and pass into the blood. The intestinal epithelial cells don't oxidize carbohydrate as the energy source because they prefer to utilize the glutamine as the energy source. Fats. Triglyceride is the primary dietary fat. It is obtained from the fat store of the plants and animals that serve as food. Triglycerol are emulsified in the intestine by bile salt and digested by pancreatic lipase to two monosaccharide glycerols and fatty acid, which are packaged in miscellaneous sublobulized by the bile salt, absorbed into intestinal epithelial cell where they are reconverted to triglycerols. After digestion and resynthesis, the triglycerols are packaged in cytomicrons which first enter the lymph and then the blood. Proteins. Proteins are digested first by pepsin in the stomach and then by a series of enzymes in the intestine. The pancreas produces precursor of trypsin, chymotrypsin, elastin, and carboxypeptidase, which are acid activated and acts in the lumen of the intestine. Aminopeptidase, dipeptidase, and tripeptidase are associated with the intestinal epithelial cell. Proteins are ultimately degraded to a mixture of amino acids, which are enter intestinal epithelial cell, where some amino acids are metabolized. The remainder pass into the blood for distribution of the other tissue of the body. Clinical correlates. Cystic fibrosis is the most common lethal genetic disease among the Caucasian population
Caucasian population.
among the Caucasian population of the population of the United States. Proteins of chloride ion channels are defective and both endocrine and exocrine gland function are affected. Pulmonary disease and pancreatic insufficiency frequently occur. Food, particularly fats and proteins, are only partially digested. Natural defecation result. Non-tropical sprue adult celiac disease result from a reaction to gluten, a protein found in grains. The intestinal epithelial cells are damaged and the malabsorption result. Common symptoms are steatorrhea, diarrhea, and weight loss. তারপর হচ্ছে digestive product in the blood. Hormone level change and glucose. Hormone level change when the produce of digestion enter the blood. 1A হচ্ছে insulin level rise, glucagon level fall. The insulin level is particularly as a result of increased blood glucose level and to a lesser extent intestine increased blood levels of amino acid. Glucagon levels fall in response to glucose but rise in response of amino acid. Overall, after a mixed meal containing carbohydrate, fat and protein, glycagon level remain fatty constant or are reduced slightly in the blood. Glucose and amino acid level the intestinal epithelial cell and travel through the hepatic portal vein in the liver. Clinical correlates. Type of 1 diabetes mellitus leads to difficulty in maintaining appropriate blood glucose levels. In untreated type 1 diabetes mellitus, insulin level are low and non-excreted because of destruction of beta cells of pancreas, usually by an autoimmune process. Before insulin became widely available, individuals with type 1 diabetes mellitus behaved metabolically as they were in constant state of starvation. Ingestion of food did not result in rise in insulin, so fuel was not stored. Muscle protein and adiposity triglycerol were degraded. Glucose and creatine bodies were produced by the liver in amounts that lead to excretion by the kidneys. Severe weight loss ensued and death occurred at an early age. After insulin became available, these metabolic decrements have been controlled to some extent. The fate of glucose in the fat absorptive stage. The fate of glucose in liver cell or other organized oxidized glucose or converted it to glycogen and tricycloglycerols. Glucose is oxidized to carbon dioxide and pani to meet the immediate energy needs the liver. Excessive needs of the liver. Glucose is oxidized to carbon dioxide and pani to meet the immediate
And water.
carbon dioxide and water to meet the immediate energy needs to liver. Excess glucose is stored in the liver as glycogen, which is used during periods of fasting to maintain blood glucose level. Excess glucose can be converted to fatty acid and a glycerol moiety, which combine to form the triglycerols, which are released from the liver into the blood as very low density level. The fate of glucose in other tissue. The brain, which depends on glucose for its energy, oxidizes glucose to carbon dioxide and pani producing ATP. Red blood cell, lacking mitochondria, oxidize glucose to pyruvate, which is converted to lactate. The lactate is released into the blood for use by the liver of glycogenesis or by the heart for energy generation. Muscle cells take up the glucose by a transport process that is stimulated by insulin. They oxidize glucose to carbon dioxide and water to generate ATP for contraction, and they also store glucose as glycogen for use during contraction. Adipose cells take up glucose by a transport process that is stimulated by insulin. These cells oxidize glucose to produce energy and convert it to the glycerol moiety used to produce triglycerol stores. The fate of lipoprotein in the fat state. The triglycerols of cyclomicrons produced from dietary fats, very low density lipoprotein produced from glucose by the liver and digested is capillary by lipoprotein lipase to form fatty acid and glycerol. The fatty acids are taken up by adipose tissue, converted to triglycerols and stores. Fate of amino acid in the fat state. Amino acid from dietary protein enter the cell and are used for protein synthesis, which occur on ribosome and requires messenger RNA. Proteins are constantly being synthesized and degraded, used to make the nitrogenous compounds such as heme, creatine phosphate, epinephrine at the base of DNA and RNA, the purine and the pyrimidines, oxidized to generate ATP. Then fasting. As blood glucose level decrease after a meal, insulin level decrease, the glucagon level increase, stimulating the release to store the fuels into the blood. The liver supplies glucose and ketone bodies to the blood. The liver maintains blood glucose level to glycogenolysis and glycogenesis and the synthesize ketone bodies from fatty acids supplied by adipose tissue. Hypoglycemia refers to low blood glucose level. Normal blood glucose level are 80 to 100 mg per deciliter. Hyperglycemia refers to elevated blood glucose levels when compared with normal. Adipose tissue release fatty acid and glycerol from its triglycerol stores. Fatty acids are oxidized to carbon dioxide and water by tissue. In the liver, they are converted to ketone bodies. The glycerol is used for gluconeogenesis. Hyperlipidemia refers to elevated blood lipid level. Normal is less than 150 mg per dl for triglycerides. Muscle release amino acid, carbon dioxide are used by the liver for gluconeogenesis and the nitrogen is converted to urea.
Fasting. A blood glucose levels decrease after a meal, insulin levels decrease and glucose levels increase. Insulin level decrease and glucose level increase, stimulating the release of stored fuels into the blood. The liver supplies glucose and ketone bodies into the blood. The liver maintains blood glucose levels by glyconeogenesis and gluconeogenesis and synthesizes ketone bodies from fatty acids supplied by adipose tissue. Hypoglycemia refers to low blood glucose levels. Normal blood glucose levels are 80 to 100 mg per deciliter. Hyperglycemia refers to elevated blood sugar levels when compared with normal. Adipose tissue refers fatty acids and glycerol from triglycerides stores. The fatty acids are oxidized to CO2 and H2O by tissue. In the liver, they are converted to ketone bodies. The glycerol is used for gluconeogenesis. Hyperlipidemia refers to elevated blood lipid levels. Normal is 150 mg per deciliter or less triglycerides. Muscle releases amino acid. The carbons are used by the liver for gluconeogenesis, and the nitrogen is converted to urea. Figure 1.2. The fasting basal state. The state occurs after an overnight 12-hour fast. The circle number served as a guide, indicating the approximate order in which the process being to occur. A amino acid, acetyl coenzyme A, ATP, adenosine triphosphate, Fa, fatty acid, Kb, ketone bodies, RBC, red blood cell, TCA, tricarboxylic acid, Tg, tricarboxyrol A. The liver during fasting. The liver produces glucose and ketone bodies which are released into the blood and serves as source of energy for the tissues. Production of glucose by the liver. The liver has the major responsibility of maintaining blood glucose levels. Glucose is required particularly by tissues such as the brain and the red blood cells. The brain oxidizes glucose to CO2 and H2, whereas red blood cells oxidize glucose to pyruvate and lactate. Glucogenolysis. About 2 to 3 hours after a meal, the liver begins to break down its glycogen stores. By the process of glyconeogenesis, the glucose is released into the blood. The glucose is then taken up by tissue and oxidized. Gluconeogenesis. After about 4 to 6 hours of fasting, the liver begins the process of gluconeogenesis. Within 30 hours, liver glucose stores are developed, leaving gluconeogenesis as the major process responsible for maintaining blood glucose levels. Carbon sources for gluconeogenesis are as follows: lactate, produced by tissue like red blood cells or exercising muscle; glycerol, from breakdown of triacylglycerols in adipose tissue; amino acids, particularly alanine, from muscle protein; propionate, from oxidation of chain fatty acids. Minor source. Clinical correlates: intravenous feeding. Solutions containing 5 gram diglucose are frequently infused into the veins of hospitalized patients. These solutions should be administered only for brief periods because they lack essential fatty and amino acids. Because of a high enough volume cannot be given each day to produce an equivalent number of calories. More naturally complete solutions are available for long-term parenteral administration. Production of ketone bodies by the liver. As glucogen levels rise, adipose tissue breaks down its triglycerol stores into fatty acids and glycerol, which are released into the blood. Through the process of oxidation, the liver converts the fatty acid to acetyl coenzyme, acetyl-CoA. Acetyl-CoA is used by the liver for the synthesis of the ketone bodies. Acetoated and hydroxybutyrate. The liver cannot oxidize ketone bodies and hence release them into the blood. Adipose tissue during fasting. Glucagon levels rise. Adipose triglycerol stores and mobilize. The triglycerol is degraded to three free fatty acids and glycerols, which enter the circulation. The liver converts the fatty acids to ketone bodies and the glycerol to glucose. Tissues such as muscle oxidize the fatty acids to CO2 and H2O. Muscle during fasting. Degradation of muscle protein. During fasting, muscle protein is degraded, producing amino acids which are partially metabolized by muscle and released into the body, mainly as alanine or glutamine. Tissues such as gut and kidney metabolize the glutamine. The products, mainly alanine and glutamine, travel to the liver where the carbons are converted to glucose or ketone bodies and the nitrogen to urea. Oxidation of fatty acids and ketone bodies. During fasting, muscle oxidizes fatty acids released from adipose tissue and ketone bodies produced by the liver. The triglycerol is degraded to three free fatty acids and glycerol. Oxidation of fatty acids and ketone bodies. During fasting, muscle oxidizes fatty acids released from adipose tissue and ketone bodies produced by the liver. During exercise, muscle can also use its own glycogen stores as well as glucose, fatty acids, and ketone bodies from the blood. Prolonged fasting. Starvation. In starvation, muscle decreases its use of ketone bodies. As a result, ketone body levels rise in blood and the brain uses them from energy. Consequently, the brain needs less glucose and gluconeogenesis slows down, sparing muscle protein. This occurs after approximately 3 to 4 days of starvation. This changes the fuel utilization pattern of various tissues enable us to survive for extended period of time without food. Metabolic changes in starvation. When the body enters the starved state after 3 to 5 days of fasting, changes occur in the use of fuel source. Muscle decreases its use of ketone bodies and oxidizes fatty acids as its primary energy source. Because of the decreased use of muscle, blood ketone body levels rise. The brain then takes up and oxidizes the ketone bodies to drive energy. Consequently, the brain decreases its use of glucose, although glucose is still major fuel for the brain. Liver gluconeogenesis decreases. Muscle protein is spread. Less muscle protein is degraded to provide amino acids for gluconeogenesis. Because of decreased conversion of amino acids to glucose, less urea is produced from amino acids nitrogen in starvation after an overnight fast. Table 1.3 summarizes the metabolic changes during prolonged fasting as compared to fasting for 24 hours. Figure 1.3. The starvation state. This state occurs after 3 to 5 days of fasting. Dashed blue lines indicate process that have decreased and red solid lines indicates a process that has increased relative to the fasting state. Amino acid acetyl coenzyme A, ATP, adenosine triphosphate FA, fatty acid Kb, ketone bodies RBC, red blood cell TCA, tricarboxylic acid TG, triglycerol. Clinical correlates. Diseases of malnutrition and starvation include kwashiorkor and marasmus. Kwashiorkor commonly occurs in children in third world countries where the diet, which is adequate in calories, is low in protein. A deficiency of dietary protein causes a decrease in protein synthesis, which can be observed through the measurement of serum albumin levels. which eventually affects the regression of intestinal epithelial cells, and thus the problem is further compounded by malabsorption. Hepatomegaly and distended abdomen are often observed. The lack of albumin in the blood leads to osmotic pressure difference between blood and interstitial spaces, leading to water accumulation in the interstitial spaces and the appearance of bloating. Marasmus results from a diet deficient in both protein and calories. Persistent starvation ultimately results in death. Both kwashiorkor and marasmus are considered examples of protein energy malnutrition disorders. Muscle use of ketone bodies decreased. Brain use of ketone increased. Metabolic changes during prolonged fasting as compared with fasting for 24 hours. Brain uses glucose decreased. Everything else is decreased. Liver gluconeogenesis, muscle protein degradation, liver production of urea. Chapter 1: Fuel Metabolism and Nutrition Basic Principles. Fat, the primary fuel. The body uses its fat stores as its primary source of energy during starvation, conserving functional protein. Overall, fats are equally the most important fuel in the body. The length of the time that a person can survive without food depends mainly on the amount of fat stored in the adipose tissue. Review test questions from 1 to 10. Examine your basic knowledge of fuel metabolism and are not. Questions 11 to 35 are clinically relevant SLM style as USMLE style questions. USMLE. For questions that required calculation of BMR values, use the approximation equation of 24 calories per kg per day for both men and women. Basic knowledge questions. Question 1 to 4. Match each of the characteristics below.